Welcome to your first Calculus 3 lesson. I'm Nick, and welcome to Cal 3, and we will be talking about a lot of interesting material this semester. We're starting today with section 11.1 in your book, which is on vectors in the plane. And so the very first thing I want to do is I just want to start out by kind of going over what is a vector. So maybe the most simple thing that I could say about a vector is let's start with a point, and we could just draw an arrow going out from that point to another point. Okay, so maybe the first point we could call that point P, and the second point we could call that point Q. All right, and if we do that, then we would typically represent this vector as we would write something like PQ and then draw a little like arrow hat over P and Q to represent that this arrow here, this is the vector PQ. All right, so something that's very interesting about vectors, though, is that the origin point of the vector P doesn't really matter. I can move around the vector in the plane, and as long as I don't change the direction or the length of the vector, we consider that to be the exact same vector. So if I were to draw another vector over here that had this exact same direction as the first vector, then I might also call this the vector PQ. Now P and Q in this point may be actually, so there's P over here, there's P over here. Those may not be the actual same point in the plane, but as long as the slope of that vector and the length of that vector are the same, we would consider them the same vector. In other words, if I had a vector here, maybe we call it U, and I have a vector here, maybe I call it V, and they have the same length and they have the same direction, then I really consider those two to be the same vector. Okay, so in this case, U is equal to V because they have the same direction and they have the same, we would call it, magnitude. So let me erase this really quick. So I want to talk a little bit about a vector in general. So one way to think of a vector, of course, is just a vector is an arrow, okay? An arrow has a length and it has a direction. But in this case, what I'm going to call my length is the magnitude of that vector. So vectors have a length or magnitude, and they have a direction. And you might think of that direction as a slope or something of that nature, but those are the two pieces of a vector, is a length and a direction. Okay, so what does it mean for two vectors to be equal? Is if they have the same magnitude and they have the same direction. They don't have to have the same starting point, and that's kind of the big takeaway here. So then we can also talk about, okay, so if a vector has a length and a direction, what if you just have like a magnitude, but it's not associated with a direction? Then you might just have a number like 4. 4 is just a number. It doesn't have a direction per se. So numbers that don't have a direction. They just have a magnitude. So 4 has a magnitude, but no direction. Okay? So numbers that have magnitude but no direction, we typically call numbers like that scalars. Okay? So 4 is a scalar. We start calling numbers like 4 scalars because we want to differentiate a scalar from a vector. So vectors have magnitude and direction. Scalars just have magnitude. So scalar is just kind of our math fancy word for saying a normal number, okay, or a real number. So one vector that's kind of interesting is what we call the zero vector. So let me write it down. So the zero vector. The zero vector, we typically just write it as 0. Sometimes we'll put a little hat on it, the zero vector. It has length 0 and no direction. So a zero vector, it's not very interesting at all. I guess you could just denote it by a dot, and that's all, because it has kind of a starting point and the ending point are the same. So it doesn't really have a direction. I guess you could kind of say it has every direction, but that isn't really that helpful. So a couple things. So we've learned we have these things called vectors. We might think of a vector just as a arrow, okay? So an arrow of sorts is what we have as a vector, but really what is an arrow? It's a direction and a length together, okay? Then we have the other numbers that we're typically using, just our normal real numbers. We call those numbers scalars because they have a magnitude, but they have no direction. And then we have this third concept, and that is the zero vector. And the zero vector is just kind of like the arrow from a point to itself, if you like. It's just a dot, but it has length 0 and no direction. Okay, so those are all concepts that we need to know. Let me erase real quick here. So let's talk a little bit about the addition of two vectors. Okay, so let's say that I have two vectors and I have a vector. Let's call this first vector the vector u. And let's say I have another vector, and I'll call this vector vector v. Then what if I wanted to add those two vectors together, and I wanted to talk about u plus v? All right. So what we typically do when we add two vectors together is I start by I take one of them, u in this case, and u kind of looks like this. And I have v that sort of looks like this. There's v. And then if I start at the beginning point of u, and then I add v, I end up at this point. So I draw this third vector in, and this one is called u plus v. Okay, so the third vector I drew, we call u plus v. And so notice that it would have been the same if I would have drawn v first and then done u. And actually, if I draw this perfectly, I get a parallelogram. Okay, so I could have done V first and then U, or U first and then V, and either way I'm going to get the vector U plus V. All right, so what if I wanted to subtract vectors? Okay, so let's say that I wanted to look at, here, let me cut this area in half. What if I wanted to look at U minus V? Okay, U minus V, well, first let's draw U. So U looks something like this. And let's say that V, okay, so V looks something like this. So negative V goes the opposite direction. Okay, so the negation of V is saying instead of going the direction of V, go the other direction. In other words, that would be going back this way. So this is, if this one is V, this one is negative V. And so I said I wanted to go U. So I go U, and then I want to go minus V. So this would be my new vector. And this one would be U minus V. Okay, so this, I go U, then I go minus V, and I get this new vector, which I'd call U minus V. All right. So, how does this work out in practice? Let's look at an example or two. So what we typically do is we write vectors in terms of like an x direction and a y direction. Okay, so I might talk about this. Like, what if my original vector starts at the origin? Okay, remember that I said it doesn't really matter where a vector starts or ends. All that matters is its direction and its magnitude. So it really could start anywhere I wanted it to. So let's just say it starts at the origin. And then let's say that it goes out, let's go out 3 and up 2. And I draw on this vector. So we might write this, let's say I call this the vector U. And so I might call this the vector U1, U2. And I use these little pointy brackets around it to let myself know that this is a vector and not an ordered pair. All right, so then I can represent U as an ordered pair of sorts, okay? But remembering that if I represent U as an ordered pair like this, that I have to remember, okay, so here's U1 in the x direction, here's U2 in the y direction. I have to remember when I write it this way, I'm really saying that the arrow is starting at the origin. And that may not always be the case, so I have to just be a little bit careful. But now let's say that I had another vector. And this time, let's call this one V. And I'll say it goes out 2 and up 3. So I'll draw that in. And let's call this one V. So I could write this as, here's a V1, here's a V2. So this is the point V1, V2. And now we could kind of talk about u plus v. All right, so if I wanted u plus v, another way of writing that would be it's u1, u2 plus v1, v2. And like I've shown you before, the way that I add vectors is I sort of take u first. So u says go over, let's say, in this case this is 3, in this case u2 is 2, in this case v1 is 2, and v2 is 3. So what I'm going to do is I say, okay, let's look at u plus v. So I'm going to go u, which is add this, and then I want to add v to where I left off. So v says go over 2 and up 3. And so here I'll put my point in. So here's u, here's v, and now I get this new vector, and this new vector I call u plus v. And what is that vector? Well, in total, what I've done is I've gone over 1, 2, 3, 4, 5, and I've gone up 1, 2, 3, 4, 5. So u1 plus u plus v is 3, 2 plus v1, v2 was 2, 3. And what I ended up with is I went over 5 and up 5. So I ended up with 5, 5. And now you might be saying, wait, I think I see what's going on here. All you're doing is you're really just adding the x components of those two vectors, and you're adding the y components of the two vectors, and that's exactly right. So this is just equal to 3 plus 2, comma, 2 plus 3, where I just added the x components together and the y components together. In other words, if I want to add u1, u2 to v1, v2, I just get the vector u1 plus v1, comma, u2 plus v2. And that is how vector addition works. Now, something that's important here is that you understand that all of these vectors right now were assumed to be at the origin. And I said that vectors don't necessarily have to start at the origin, but if they do start at the origin and you know the form of your vector when they both do start at the origin, then this works out quite well. Okay, let's do one more example like this just to see how this works. So let's say that I have a vector u that's equal to 4, 3, and I have a vector v that is equal to 2, 5. Then I could ask the question, what is u plus v? And the answer is, well, u plus v is 4, 3 plus 2, 5, which is equal to, now I'm going to add the x components together. So I'm going to add 4 plus 2. Then I'm going to add the y components together, 3 plus 5, which is going to give me 6, 8. So in this case, u plus v is the vector 6, 8. Again, assuming that the starting point of my vector is the origin. Now, what if I wanted to figure out what's u minus v? Well, minus v is going in the opposite direction of v. So if positive v is 2, 5, I know that positive v is 2, 5, then negative v is going to be the other direction, or negative 2, negative 5. Okay? So in other words, if you have a negative in front of a vector, you can just negate each component of that vector. But now we can look at u minus v is the same as u plus, well, whatever negative v is, which is u is 4, 3, and negative v is negative 2, negative 5. So I add each component, and I get 4 minus 2, 3 minus 5. So I end up with the vector 2, negative 2. Okay, and if in doubt, draw the picture. U goes right 4, up 3. Negative v would go down 2, left 5. And where would you end up? I think that the answer would be you would be at 2 minus 2. And that's exactly right. And so that is how you add two vectors, provided that each of those vectors starts at the origin. Now, if a vector doesn't really start at the origin, then what do? We probably need to figure that out, because we're not always going to deal with vectors that start at the origin. So let's say that I had a vector that started somewhere. Okay, let's start with a point. Let's call this the point 2, 3 in the plane. All right. Then, what if the second point was, let's say, up here at, let's say, 6, 5. Okay. Then how could I write this vector in component form? Well, let's see. Let's set up an xy axis here and try to so this is 6, this is 5, this is 2. I guess I didn't draw this perfect, but this is 3. And so what do we got here? Well, what we really want to do is, if we wanted to set this vector on the origin, then we'd need to move it down 3, and then we'd need to move it over 2. But the one that represents it is going to be its final resting place, which in this case is 6, 5. So we need to move 6, 5 down 3 and over 2. And that's going to give us our standard form of that vector. So if we want to put this vector, I'll call it u for right now, into standard form, u is going to be equal to, well, 6, which is where it's starting, but we need to move it back 2. So I'm going to subtract the starting component, or the starting point. Then I'm going to take 5, and I'm going to subtract the y value where it started, which is 3. And I'm going to end up with the vector 4, 2. All right. So if I shifted this thing down 3 and I shifted it back 2, then I'm going to end up with the vector 4, 2 in component form. Let's try that one more time just so that you can see another example. So let's say I had a vector that started at, let's say, the point 2, 1, and then it pointed to this is the point 1, 4. Okay, so what I'm going to do is I'm going to take the point that's being pointed at and subtract the initial point from it. So if I want, let's call this V. So if I want to find V in kind of its component form or its pointy bracket form, then what I do is I'm going to take the ending point in the x direction, which is 1, subtracting the starting point in the x direction, which is 2, and then I'm going to take the ending point in the y direction, which is 4, and subtract the starting point in the y direction, which is 1. So what will I get? I'll get -1, 3. Now, if I took this vector and started it over here, this vector goes up 3 and left 1. Up 3, left 1. This would be the exact same vector. And what is the point at which it terminates? Well, it's -1, +3, which is exactly what I came out with. So we just took that vector that was not starting at the origin and shifted it in such a way so that now that vector, same vector v, but now it's starting at the origin and has these two nice components. Okay, so that's something that we've got to be able to do right off the bat, is we've got to be able to shift these vectors in such a way that we can see what they would look like if they started at the origin. All right. Now, how do we find the length of a vector? So the length of a vector is really just the distance between 2 points, right? And we know how to find the distance between 2 points right now. We have a distance formula, and the distance formula that we've always had is that the distance between 2 points is equal to the following. So let me say down here that I have 2 points, and this, let's call this point x1, y1, and this is the point x2, y2. Then if I want to know what's the distance between those 2 points, d, we have the distance formula, and the distance formula says it would be the square root of x2 minus x1, quantity squared, plus y2 minus y1, quantity squared. All right, so that's how we would find distance between the 2 points. But in this case, if we wanted to call this the point P and this the point Q, let's see, that's not really a Q, is it? And so we call this the point Q, then this would be the vector PQ. And if I want to say what's the length of PQ, then I put kind of like these absolute value bars around it, but that's not going to stand for absolute value when it comes to vectors. We're going to call that the magnitude of vector PQ. In other words, the length of the vector PQ. Now, it actually has something to do with absolute value. There are some similarities, and that is that absolute value actually tells you how far is something away from the origin. Okay, and really what this is saying is how far is the terminating point of this vector away from the origin if the vector starts at the origin. Okay, so they are similar in a way, but don't think of this as an absolute value when it comes to vectors. Think of it as the length of the vector, or if you want to call it the magnitude of the vector. And the way we're going to find the magnitude of a vector is right here. Okay, let's just try one really quick so you can see how this works. So let's say that I have a vector where the point P is at -1, 2, and the point Q is at 3, 3. Then let's find the length of the vector PQ. Okay, so if we wanted to figure this out, we want, in other words, the length of PQ, or another way of saying that is the magnitude of PQ, is going to be equal to the square root of x2 minus x1. x2 in this case is 3, minus x1 is -1, so 3 minus -1, squared, plus y2, 3, minus y1, 2, quantity squared. So this is equal to the square root of 3 minus -1 is 4, so this is 4 squared. 3 minus 2 is 1 squared. So what do we got here? We've got 6 underneath the square root. I've got a 16 plus 1, or this is the square root of 17. So the length of that vector would be the square root of 17. Make sense? Hopefully so. Now, another thing that I need to cover with you and make sure that everybody understands is that you can multiply a vector by a scalar. So you can talk about something like 4 times v. Now, let's say that I have a vector, and let's say that that vector is the vector 1, 2, and I want to talk about 4 times that vector v. Then what I want to do is, really this is the same thing as saying v plus v plus v plus v. Or in other words, I take v and go v again and again and again. And what would I end up with? Well, I go right 1 up 2, right 1 up 2, right 1 up 2, right 1 up 2, right 1 up 2. Where would I end up? I would end up at the point up here. That would be the point 4, 8. Okay, so in other words, 4 times 1, 2 is equal to 4, 8. So I can multiply each of the components of the vector by 4 and get the resulting vector. In other words, if you have a constant times u1, u2, that's just the same as that constant times u1, that constant times u2 as a vector. So I can just distribute that constant across the vector, or in other words, I can multiply a vector by what we call a scalar and just get a new vector out. Make sense? So let's do another example really quick. So let's say that I have 2 vectors. So let's say I have u is equal to, let's say 1, 2, and v is equal to the vector 2, 2, 3, then what if I wanted to find 3u plus 2v? Well, that's 3 times 1, 2 plus 2 times 2, 3. In other words, I can multiply through using scalar multiplication of a vector and get that this is 3, 6 now. Plus, I can multiply through again using scalar multiplication of a vector and get that this is 4, 6. But now adding those two vectors, I just add them up component-wise, and I get that this is 7, 12. And so 3u plus 2v in this case is the vector 7, 12. All right, so another important concept that we need to talk about when we talk about vectors is just the concept of a unit vector. Okay, so what a unit vector is it's just a vector that has length 1. Now, if I have any old vector in the plane, so let's say it starts at the origin and I have a point out here that's its terminal point, and I have that vector u, it has some magnitude. But what if I wanted to know what's the exact same vector that has the exact same direction as this vector, but instead I only want to go out 1 unit? So if this had just length 1, then what would the vector be in the plane that had exactly length 1 instead of having the length of the vector u? Well, there's a very easy way to find this. And the way that you're going to do it is, if you want a unit vector, you take u and you're going to divide u by, for some reason my pen is not working, just one second. You're going to take u and you're going to divide it by the magnitude of u. And this will give you a unit vector with the same direction as the original vector u. So really what you're doing is you're taking u and dividing it by its length, which will give you length 1. So if you want to find a unit vector, then you have to start out with some vector, find its magnitude, and then divide that vector by that magnitude. So let's do an example really quick. Let's start with a vector u, which is equal to, let's say, the vector, let's say 4, 5. And let's find a unit vector with the same direction as u. Okay, in other words, what we really want to find is we want to find u divided by its magnitude. In order to do that, we need the magnitude of u. And the magnitude of u is the square root of, well, it's x2 minus x1, but this is already in standard form. So the x1 and the y1 are both just 0 and 0. So this just becomes very easy, and it's just 4 squared plus 5 squared. Okay, so what does this become? This is the square root of 16 plus 25, or this is the square root of what? 41. So if I want my unit vector, it's going to be u divided by the magnitude of u, which in this case is u, which is 4, 5, divided by the magnitude of u, which is the square root of 41, which really could be written as 1 over the square root of 41, that's a scalar, times 4, 5, which also could be written as 4 over the square root of 41, comma, 5 over the square root of 41. And so here's a unit vector that has exact same direction as my original vector, u. Very good. Okay. Let me cover real quick some of the properties of vectors that come out a lot. And then you should be about ready to look at some homework questions. And that is that just some simple things that you see when using vectors is that u plus v is always equal to v plus u. Okay, so vector addition is commutative, in other words. This is the first one. Second, we have that u plus v plus w is the same as u plus v plus w. In other words, the associative property holds. 3, if you add the 0 vector to any vector, you just get the original vector. Also, if you subtract a vector from itself, you get the 0 vector. Also, you can multiply the addition of two vectors, u plus v, by a scalar, and that scalar will distribute over that addition. So you could write this as cu plus cv. 6, we have that a plus c, two scalars added together, times a vector v, is equal to av plus cv. So in other words, a vector can kind of distribute over scalar addition. Next, we have that 0 times v. I'm sorry. I didn't want a vector symbol over that 0. This is just 0 as in the actual number 0. So 0 times v is the 0 vector. 8 is that a constant times the 0 vector is always the 0 vector. 9, 1 times any vector, where 1 is a scalar, is just the original vector. And finally, number 10, I'll write over on the side, is that a constant times a constant, so a scalar times a scalar c times a vector v is equal to a times c times the vector v. Okay, so, and we call that the associative property of scalar multiplication. So all of those are helpful, and all of those should help you to put together vectors and be able to do some interesting computations with vectors. I think now it's time for you to start trying some homework. Just start playing with some vector operations, see if you can add, subtract, multiply vectors by scalars and such, and that gives you what you need to get started. So Your homework 11.1 is ready to start. If you have any questions, let me know. Thanks.